I took pictures. I'll get them.
Okay.
I got it.
So this is the, no, wrong class, Rich. I keep getting y'all for one of my ILT courses. I don't do very many INT courses. So what was missing, this is not it, Rich. So what was missing was this line right here. And plus, on my drawing, I had an exhaust over here, which couldn't be, because everything's got to be lined up in its at-rest position, right? So here the at-rest position is to the left because the spring is over there on the right. Okay. And then these are pneumatic control. These are pneumatically controlled pilot-operated valves, single pilot-operated valves. I think Omar, you was having problems because you was using double pilot-operated. So what was going on is the way Wendell had his hooked up is he put a T right here and tapped off the shuttle valve and run it into port 1. From what I know, and he did the same thing over here, which that's not even in the drawing. So this is the way it's supposed to be. So what's our shuttle valve doing? What logic is it doing? So we talked about 5 different logics. We talked about and, or, nan, nor, and not. Normally closed 2-2 would give you a not. Now this guy does an or. And then your dual pressure. So that means either this one or this one. Either one we do is going to shift that shuttle valve, and it's going to come over here and cause this guy right here to extend, or it's going to cause it to shift. So it should be in the retracted position if we hooked it up right. Now y'all supposed to do what? Y'all supposed to label everything with the labels and also number the ports. So over here, the pressure port, I didn't have a pressure port over here is what I didn't have. And of course, so no matter which way you do, whichever one of these buttons you press on these manual operated 3 two-way valves, it's going to shift this shuttle one way or the other, right? Which is going to cause this guy to shift. So what's going to happen is I press either button, it should cause that to extend, but then it should do what? Retract. The problem is we didn't have anything to retract it, because when I let go of the button, there was nothing coming out of the shuttle valve, and if there was nothing coming out of the shuttle valve, then there was no pressure coming into here. So what was happening is people was taking the output of this right there and running it into 1. So as long as the shuttle valve was shifted or had pressure on it, then it would extend. But as soon as it started retracting that air exhausted, then the thing wouldn't extend, wouldn't come back and retract for it. So that's what was going on. And of course, this is a dual pressure valve, and it does and operation. That should have been on this test, by the way, but I thought there was enough on it already. So these will definitely be on the next test. And what does a dual pressure valve do? It does and, right? Now I could take the output of an and then run it into a normally closed 3-2, pneumatically operated. Not 3. Yeah, 3-2 or 2-2. Either one would work. And then that would, if it was normally closed, that would give us a nan and a nor, right? And then a normally closed valve would give us what we call a not. So we can get all the 5 basic logic functions using these pneumatic cylinders. So if we can do those, then we can do anything. So all digital logic consists of those 5 basic functions. I don't care what it is, whether it's a counter or whether it's a flip flop or whether it's a one shot or anything like that, they all deal off of 5 basic buttons. And I think the guy said on one of the videos that y'all couldn't hear, that there's nothing that we can't do with pneumatics that we can do with electrical control systems that I know of.
And something, I guess, this class or before we take the next step, not the relay, we definitely going about logic. I think I got a couple on adding on to make it.
Yeah, so.
You know what I'm
Yeah.
saying? So, I didn't know if that's how it would be on the test or.
Well, what we need to do is one shuttle valve gives us only 2 inputs, but how many things might we want to order together? 2 more, 3 more. So what we can do, and this is also true in digital logic, is what we can do is I can take, so the 2 signals I want to order together, I would bring into my shuttle valve. Okay, so that gives me 2. But what I could do is I could take the output of this and bring it into another shuttle valve. No, I don't know why. I'm drawing these fast, guys, so they're not going to be pretty. So what would that do? That would simulate a 3 input OR, right? Understand? And then I could take the output of this one, and we could keep doing this as long as we got them. So we've got one valve over there that's got 3 shuttle valves in it. We got one in one unit. It's got 3 shuttle valves, and we got another one that's got 3 dual pressure valves in it. So this would be A input, B input, C input, D input. So now I'd be able to OR 4 things together. These are ORs.
That's a, I want you to draw again on, you can get a copy of it.
What?
So,
The symbols?
get a symbol.
The digital symbol for an OR is this. Now, and then of course, so what we're doing here is we're doing this. Now in digital logic, this is oh, I did that wrong.
But which would be on the digital logic or?
No, what would be on the test is the shuttle valve. All we're doing is how this would be represented in using symbols. But this is kind of misleading too, because in digital logic, we can buy 4 input OR gates. So in digital logic, I would use one of these. But the problem with shuttle valve, we can't do that because the maximum on shuttle valve we got is what? 2. So what we would have to do is we would have to do it like this. I could do it like this too. And we do that every once in a while because when you buy a logic gate, it comes in a package. And then if you got and they're going to come with a certain number of inputs.
You start off with an OR and then you go to an AND.
No, it's still an OR.
It's still an OR.
Yeah, because that's all we're doing is OR. So we're saying, okay, if I come up here and put pressure in right there, and I put pressure in right there, it's going to cause that to shift. It's going to cause this to shift, and I get an output. If I come over here and put this, it's going to cause this to shift. It's going to cause this to shift. We're going to get an output. If I come over here and press right there, it's going to cause this to shift. We get an output. So no matter which one we bring our input in, now we're ORing 4 things together. But what we have to do with shuttle valves is we have to stack them like that, right? You understand? So I could have, but every time we add one valve, we only get 1 additional input. So we get 2 on our first one. We add the second one, we go to 3. We add the third one, we go to 4.
So they're on the max initial.
Yeah. Every addition one, you only get one more input on your OR. Now, I could come up here and change this to dual pressure valve too, and it would do exactly the same way. All I would do is just take the output of a dual pressure valve. So we just change the symbol a little bit, right? So I come up here and change this to a symbol for a dual pressure valve. And then I change this to a dual pressure valve. Oh, I need to get rid of that line. My flow lines. I don't think there's a simplified symbol for these things. So I come over and put pressure right here. I put pressure right here. That centers this one. It comes up, puts pressure right there, but this is still zero pressure. So this guy's going to shift over here, is going to block it off, right? You understand? If I put a zero pressure right there, this guy right here, we don't have pressure. We got zero pressure there, zero pressure there. We get zero pressure out. So the only way this is going to work, if I do what? Put pressure right there, that's going to center it, let it flow through. I put that's going to let pressure right there. I put pressure right here, and that's going to center it, let pressure flow through. I put pressure right there, that's going to center it, put pressure through, and I'll get pressure out. So now the only way I'm going to get pressure out if I have pressure on all of those inputs. So, or we use the term any. So if I have pressure on any input, we get an output. On and, we use the term all. So if I get pressure on all the inputs, then I'll get pressure on the what? On the output. Now the symbol for that is the symbol for an and is it's the shape of a D, like this. Now how I would get a NAND is I would take the output of this one and then I would run it into a pilot operated valve. Right, you understand? Now, I'm just gonna draw one like it's acting a single acting cylinder instead of a double acting cylinder. So I'm gonna come over here, and what I'm gonna do is I'm gonna put this right here, and then I'm gonna put this right here. So what happens right now, if this was a zero, it's gonna do what? I'm sorry, I got it backwards. I'm trying to get an output when we're trying to cut it off when we get an output. Yeah, the close should have been on the side. You're exactly right. Of course, now we bring in pressure right here, right? And then we would close it off on the side. So now when the output of this goes, so now we got pressure all the time. But when we have an and, that'll push it over and stop the flow. So this would give us what we call a NAND. A NAND. A NAND is this symbol right here. So that's all the logic. So I can do NANDs. I can do if I do the same thing with shuttle valves, then I get a NOR operation. With the AND valve with the dual pressure valves, I get a NAND operation, and that's all three of them. And that one on the top would be an inverter, right? You understand? That's what it does. It would be what we call an inversion, or not. It's kind of misleading. Inverter is the name of the circuit. Not is the name of the logic. So we have 5 basic logics. We got AND, OR, NAND, NOR, and NOT. And everything in digital falls into that. So that means we can do just about anything we want to with pneumatics. So the only thing we can't do is math. We can't add 2 things together and stuff like that. But we don't do that with electrical controls anyway. So if you hear what people say, it says there's nothing in electrical controls that we can't do in pneumatics. Anytime I do math, we got to add computation. So that's one advantage a programmable logic controller has. It's a computer. So not only can it do logic, it can do math. It can do compares. It can check things out. So that's the big advantage of a PLC is it adds that computer in there. So if I change these over to, if I change the valves over to, a lot of my valves over to the solenoid controlled valves, then we can let a programmable controller shift the spool. If I do it with a programmable controller, it's a computer. So we can not only do, yes and no's, we can do.
What would make the PLC lose program?
So you got bad memory. The PLC has a little battery in it. And if you leave it off a long time, it's going to lose its program.
We have
So we
another machine that servo motor. And I guess probably about 2 years after we had it, the PLC started. So they're telling you something.
Well, if it's on all the time, you don't have that. You shouldn't have that problem. You just got to.
Well, when it was on, we have power loss.
Yeah.
You know what I'm saying?
Well, see, they need to go back. They need to change the batteries out. You probably need to change the batteries out in those PLCs at least once a year. And that's rule of thumb for robots too. Robots have batteries in them too. They keep what we call the origin. So it's like when you give directions, you don't say, well, go down 5 blocks and turn left, because you always have to start it from somewhere, right? You understand? So a robot has what we call an origin. That's the factory presets it, but you can make it anything you want to. And once you set an origin, everything you teach that robot is from that reference point. And if you lose that origin, none of your programs are going to run anymore. So all your robots have batteries in them too. And if they hadn't been changing those batteries out, and they lose power, if they lose power to those robots, they're going to lose that origin. And if the company used the factory origin, probably okay. But if they do their own origin, it's like Lincoln. Lincoln, when they put that welding torch on there, normally the origin on a robot is with the arm straight out. But if you put a welding torch back on there, that wire is going to come on the back. So Lincoln had to put their origin down like this. Well, if you didn't know that and you lost the origin, and why I bring it up, our welding instructor, this happened. So he lost the origin on the robot. What did Rich do? I went in, I set it according to the factory, right? And it missed everything by so far. And we called Lincoln and he said, well, that's not the right origin. We did our own origin. So yeah, those PLCs have batteries in them, and they're usually pretty easy to replace.
We just, they didn't figure out what was going on with it.
Yeah, you need to say. Now you sound funny.
Oh,
So
I
you
know
know
now.
they got batteries in it.
You know.
Of course, that might not be it. It might be the memory's in it loose or something like that. Sometimes they have these little SIM cards because they don't have enough memory in them. So a lot of them you can buy these standard SIM cards and plug them in there. But you can't use one for a computer. It's like in my camera, I got a Nikon camera. Well, if I took my Nikon camera out and put it in a Canon camera, it's not going to work because it's formatted different the way it's set up. It's just like the SIM card in an iPhone and a SIM card in an Android are the same, but they're formatted different, so they won't work from one phone over to another. So if it's got a SIM card in it, then you might want to reseat that. It might have got a goop in it. It might be using that memory if it don't have enough. And they need to have backups for all their programs. So they have somebody that come out and do that for them.
You know,
Charges them a little bit of money, huh?
and one of those little bit, this dude coming from Germany,
Siemens?
Herzog.
Herzog?
Herzog.
The name of the PLC?
Now, yeah, the PLC was Siemens, but because it was under warranty, they called people who, because they specially built this little machine, for the test that we were using. They called Herzog. They can't. They repair.
That's very unusual.
Pointing that stuff at each other the whole day. You know what I'm saying?
That's very unusual that they would send. So English is a second language over there. We were over in Berlin, and we didn't have any problem. The whole time we was in Berlin.
Really?
I mean, every restaurant you went into, somebody there spoke English. In fact, Siemens schools are in English.
Right.
That's what's so strange. So if you took any of the Siemens schools from Siemens, they teach only in English. Okay, guys, y'all go ahead and take another 2-minute break. So we looked at rotary actuators, and this is our symbols. We have hydraulic symbols and we have pneumatic symbols. Everybody okay? Now, the pneumatic symbols is the actual symbol for the compressor itself. This is not the symbol of the tank that we stored in, right? Usually that has another symbol. And then we have bidirectional, we have a fixed displacement, we have variable displacement, pressure compensated, and then of course our rotary actuators. They call them partial rotary motors, which is okay. And I saw another place where they called it oscillating motor, because it just goes back and forth, back and forth. Just to avoid confusion, we'll just call these things rotary motors. And then I think what I was looking at last is
Go back to that.
this. Are we okay? Okay, Ron? So these are our formulas. These should be in that formula sheet that I gave out. These are right off there. The only thing that's different is the conversion for pneumatics. So pneumatics we usually use 29 or 28.8, and fluid power we usually use 231. Everybody know where those came from?
So,
Well, what happened is these are the conversion factors to go from gallons per minute over to cubic inches per minute. So 28.8 or 29 goes from cubic feet per minute over to cubic inches per minute. And 231 goes from gallons per minute over to cubic inches per minute, right? Does that make sense? So there's your two conversion factors there, 231 and 28.8. A lot of books you'll see teach 29 because this is kind of loose, and that's closer and easier to remember anyway. Are we okay? So if you look at RPM for hydraulics in the formula sheet, it's going to say 231 times gallons per minute over displacement on cubic inches per revolution. So cubic inches on top, cubic inches on bottom, so everything is going to cancel out, right? That makes sense? Are you okay? So the formula sheet, basically in that formula sheet, any place it says 231 for hydraulics, you can replace it with 28.8 or 29 for what? Pneumatics. Yeah. So all those formulas are basically the same. So somewhere we got hydraulic RPM. Are we okay? So I think every one of these came right off that formula sheet. This is what we call a gear motor, and this is the one I passed around in class. Everybody okay? I need to say that again. Gear motor. Huh? Everybody okay with gear motor?
You said you got an example of it?
Oh yeah, turn around, look. Slide right.
Right here.
Yeah, both of them. The one standing up and the one that you have to take apart. But if you look at the one standing up, you'll actually be able to see the two gears in there. And they basically just mesh together. And so what happens is your fluid comes in on this side. What's it going to do? It's going to push against these. It's going to cause us to what? Rotate. And over here it's going to do what? This says in it. They got the arrows flowing wrong. Oh, this is a geared motor, but they got it drawn like a pump. By the way, what you find out is that in fluid power, just about every motor can be used as a pump or a compressor. So we have different types of compressors, but this is true. So this is a very, very popular pump also. A geared pump works exactly the same way. Now remember, your pump don't really create pressure. What does it create? Flow.
Flow.
And then when that flow hits against something, it causes what? It causes pressure, and pressure causes the force. So we can't have force without pressure, and we can't have pressure without force. But you need to understand the two, right? This is a pretty good picture of an external gear motor. And of course, one of them is going to be the driver, and the other one's going to be what we call the dribbling. Some people call it an idler gear. Yeah, so you can actually see this one. So it's got the rod or the axle coming out, and that's where we would actually get our drive off. Of course, both of them create torque when they turn, because this one is pushing against that one. This one is actually pushing itself, but this, whatever torque is being produced with this one is also pushing into there. And then the meshing of the gear is what seals you in the center. Are we okay? Then we have what we call an internal gear motor. Operates inside one of the other inner gears, has one tooth less. So your inner gear has one tooth less than the outer gear. So you'll come up and you end up with something like this. So what happens is this guy right here turns around the outside. So fluid comes in and does what? Pushes against this side, right? Y'all see that? It causes it to do what? Move. And this is going to slide into this one. This one's going to slide into this one. So what they're saying is we always have a what? A seal between the in and the out. And this is called an internal gear motor. So what happens when that center gear starts turning, it causes the what? The outside gear to turn. Are we okay? Yes, no? This is called a vane motor. This is very popular in pneumatics. So what we got is we got these little old tabs that stick out all around. And then usually they have a spring in here that holds the vanes up against the side of the motor. And then of course all it does is basically do what? Push against those vanes. Are we okay? Make sense? Well, when you push against the vanes, you got pressure, you got area. You're going to create what? Force. If we create a force, then we're going to create a motion, right? Here, the motion is going to be what? It's going to be a rotary motion. And like I said, vane motors are very, very popular. So this is a vane motor, but this is the what? So here's the rotor right here, and here's the vanes. The vanes sit inside little grooves right here. And then what happens is it works the same way. It comes in, pushes against the vane. When it pushes it again, it causes it to what? Move. Then we seal it up. This one pushes around. Then it comes around to the other side, and it's actually exhausted, right? You'll see what. Huh? This probably is not in there. This is probably, I just added this. Because I was saying, well, man, my impact wrench uses pneumatics. So get a cutaway and see exactly what type of motor it uses. And it turns out it uses what? Just uses a vane motor. Of course, it's got that hammer assembler in it, so if it bogs, it'll slide up and then drop back in and cause it to shock your screw. In the old days, we used to take a hammer and bop on them to do what? To break them loose. Or heat them up. Just heat them up too. Cause them to expand, and then you throw water on them, cause them to do what? Well, right, we used to do that. Doing what?
I didn't have it. I didn't have a crane hold up the assembly. I was underneath it, taking the screws off, and the last screw dropped from under it, came down.
Oh.
Knocked it out of my hand.
The wonder it didn't crush your hand.
Yeah, I was lucky. I was very lucky.
Yeah, so this is showing the seals. And so what happens is we have open on one side, and then we come in, we push, then the vanes start moving, the fluid gets trapped between the vanes, and when it comes on the other side, it does what? It ejects the motor. And you can see this could also act as a pump. So if something's spinning those vanes, right, it would create a low pressure. Then you got the pressure on the other side that would just pull it in. So sometimes they set them off to the side. So this is what this is doing, vane type motor. This one is basically centered. See the difference how they work though. Everybody okay? This tries to show the springs that's holding up against the sides. That's a pretty good motor. This looks like it's got two vanes in it. Then we have a piston motor. That's what this guy is right here. And what this does is it works against what they call a swash plate. A swash plate is basically a plate that's at an angle. So y'all can look at this right here. So you can look at these motors and you can see it's got that curve. And so what it does is that those pistons are moving at an angle. So what happens is I come in here and I push in on that thing. It's going to come up here and push on that angle and cause it to rotate. And then when it rotates, it's going to go against that plate. It's going to force those pistons out. And then what's that going to do? That's going to cause it to exhaust. So ain't that neat? This is called a piston motor. We could also use this as a pump. Now, I don't know if they show this or not. What we can do here is that if we can move this outside. So if I had the ability to move this outside, since this thing right now is off-centered, the more I move this to the center, the displacement would go down. Right? You understand? Yes or no? Understand? Right? Yeah. So we can have what we call, so a vane motor can be what we call a variable displacement motor, which means what we can do is notice this thing's on all sides. So this would be the displacement set right in here. This is where it's getting all this pressure. Well, if I move this up, then what this up here is going to be, it's going to be smaller, and we're going to change the displacement. If we change the displacement, then we're going to change the speed. Right. If displacement goes down, what would you think speed would do? Go up. But torque would go down, right? You understand? So speed goes up, torque goes down.
So, what we talked about is hydraulic.
Well, this pneumatic. This is a vane type motor. Is this hydraulic or pneumatic? Either. I mean, I just showed you my impact wrench, and this uses a vane motor, right? You understand? Now, what we do on that impact wrench is we control the flow. We have a variable flow valve on that. But what we could do here, if we could shift the outside, then we could change the displacement. If the displacement gets smaller, the speed would go up, but the torque would go down. What's nice about using a flow control like your impact wrench is that if the flow stops, then the pressure goes up real high, right? If it is flowing, the pressure. So on this guy right here, if I could change that angle, then I could change the displacement. If I could change the displacement, then we would change the speed, right? But we're not, or the torque. So we slow the motor down, we get more torque. We speed the motor up, we get less torque, right? But more speed. But all we need to do is change that angle of the motor. Now this guy here has a fixed displacement, but we got to.
Show it over there.
Right, adjustable. We can change that swash plate, and we'll go over here and look at it. So this is a fixed displacement. And this is showing you basically how it works. So what happens, we come up here, we push pressure in here, right? You understand? And then it would do what? It would force this thing out. It would cause it to spin. I think this is backwards. This looks like a pump. This is a pump. So notice what happens is the fluid comes in here, and then when it turns, what's it going to do? It's going to suck the fluid in, and then when it gets on the other side, it's going to go down and push it out. All we need to do on this one to make it a motor is change the what? Direction of the arrows. And this is showing the inlet ports and the outlet ports. This is people. So one side we're going to be pushing in, and the other side is going to start going down. So you notice it's down half the time. It will do what? It'll push the fluid out on the other side, and it'll come back and just repeat that. Are we okay? Yeah, this is a pump, but all you do is just change the arrows and then make it a what?
Change the arrows to make a motor.
Motor, yeah. And that's what's nice. It's like most DC motors. DC motors are really neat. Most DC motors, we can run them as a generator or we can run them as a motor, which is pretty neat. AC motors, induction motors, you can't do that. Synchronous motors, you can do that.
Okay, the whole thing about it, I'm trying to get the whole gist of this thing. You got piston B, you got piston A.
Yeah, but we got bunches of pistons. They're showing us two. If you look at this thing right here, Brian, that's a piston motor.
Okay, so the advantage of this is that it's because of its position in moving the hydraulic in and out as the motor turns.
Right, we're pushing in on one side, and it's exhausted on the other side, right? It's just like your car engine. But this right here determines, so what happens is that right between here, it changes from what? From pushing it out to do what? Bringing it in. So when we come right here, we hit this point right here, this guy right here is in this compressed condition right here. And then we start bringing pressure in, what's it going to do? It's going to push this up, but it's working against a plate that's at an angle. So what it's going to do is it's going to cause it to rotate, right? You understand? And it's going to rotate, and then it's going to get right here. Now, as soon as it gets right there, it goes on the other side of the swash plate, and it starts pushing the piston down. So it moves right here, and then the piston now is starting to go down by the force going up on the other one, and it causes it to do what? To push it out, right? You understand? So this is the motor. And then it'll push it out. Then it bottoms out right here. So the piston would be at its lowest point, and then it'll move back here, and then the fluid power is going to start doing what? Pushing the piston in. Huh?
I've been working on the problem for a while, gravity problem, and I just said, where we get the weight from. I thought about something like this to push a car uphill.
Well, you still have to have a prime mover.
Yeah, because see, you're going against gravity, and this almost would solve it if we had enough weight to push down. It would almost.
But you're going uphill.
Yeah, because we're going uphill. And so, I'll just think about it some more. But something like this, hydraulic working for you like this, is just about to solve that problem.
No.
Well,
You're trying to go up hill without producing energy. Now we can coast downhill because what helps us coming down? Gravity. Going uphill, gravity's working again. So what you would have to do is you would have to create more energy. You would have to create more energy than you're consuming. You'd have to create more energy than you're consuming. So it'd be like moving a sailboat with a fan on the sailboat.
But that's the idea.
Yeah.
Well, y'all laughing.
That's all business now.
But see, you would never think that we can put, 3 tanks in a plane and take off as heavy as we.
Yes, I would too.
Not 50, 60 years ago you wouldn't, 100 years ago you wouldn't.
As long as you create, but you're still consuming more energy. You're still creating more. You're still using more energy than you're producing.
But in the motor, your high torque is what gives you energy, correct?
What's that?
High torque is what gives you energy to get the motor to turn. What's creating your energy in the motor? Like, you up against this pressure, you got to get it to move.
That's right. But there we use a camshaft. This is kind of like the same thing. But instead of the camshaft pushing it in this direction. So what happens on your engine? Of course, what you do is you fire your spark plugs, and it makes extreme a lot of heat. And what does that do? Cause the air to do what? When air gets hot, what does it do?
Pressure.
Creates pressure, right? Pushes down, causes it. So people think it's the gas that's moving. No, it's the heat. You're sucking air in. You heat it up real fast. What does it do? Expands, right? As soon as it expands, it creates a lot of pressure, pushes down on that thing, and then it's transferred over to a drive shaft. But still, you're consuming more energy than you're producing. So your horsepower, the horsepower in your engine is not the horsepower you get to the wheel.
Right.
Y'all understand that?
Yeah, it's always gonna be less.
Always going to be less. So that's the problem you have. You're saying I need to turn what are you going to turn? What are you going to turn the motor with, or what are you going to turn? What are you going to turn the hydraulics with? Well, whatever you do to turn it with is going to use more energy than you produce.
Right. Well, that's
I mean, if you can do that, Franklin, you'll be supporting all of us. You have a lot of friends. Kind of like SpongeBob. I don't know if y'all saw that one, right? Let's go over here and look at this variable.
All right, guys, lab number 12. Now we're getting into some interesting stuff. Anything you can do electrically, you can also do with pneumatics as well. You want to make an on-delay timer? You can definitely do that. You just need a few components, similar to what you'd have in a standard electrical timer. The components that I'm going to show you are similar to a resistor and a capacitor. Resist the flow to the capacitor. The capacitor gets to a certain voltage and then sends a signal to turn on. Same thing we're going to do here. We're going to have a flow restrictor with a holding tank, and the holding tank is going to act as our capacitor. Okay, let's take a look at the circuit and what we're being asked to do. Use a 3-2 push button and a 5-2 pneumatically operated spring return relay and a double acting cylinder. Okay, so push button controls a 5-2 pneumatically operated relay, and that relay then controls our double acting cylinder. Provide a delay on signal circuit in which you press and hold your 3-2 push button. And then after a 5-second delay, the 5-2 relay is going to change state. When the 5-2 changes state, the double acting cylinder is going to extend. As soon as you let go of the push button, the double acting cylinder is going to retract immediately. So it's exactly the same as an on delay timer. Press and hold the start circuit. It takes a little bit of time before it changes state. As soon as you let go of that signal, it reverts back to its rest state. Okay. If you're Googling this, you will find that they'll come up with this diagram here, very similar to what we're going to do. But again, we do not have 3-2 pneumatically operated valves. We're going to replace this 3-2 with a 5-2. Okay, let's take a look on the fluid sim. All right, guys, so let's build this up nice and slow. We need to have one of these signals coming in. Let's do the rest state as a retract. Right, so here's our main compressed air coming in. And in the rest state, being denoted by this spring, air would come up, push this guy back, and then we just need a path for that air to exhaust out. Looks good. We're also going to provide our 3-2 with some air there. Okay, looks good. I think if I gotta drop this down, otherwise I'm gonna have superimposed lines. We'll see how it works out. Okay, so we have the 3-2, and now the signal going into our 5-2, we're now going to create a timer using two components. We need to have a holding tank, and we also need to have a flow restrictor. So let's drop down here. The flow restrictor was right here, the one-way flow control valve. Okay, and let's see if this guy is going to work. Let's see, right here. Looks good. We'll move this bad boy over here. And move this guy over a touch. Looks good. All right, so you can see that we have a one-way flow control valve. We have a holding tank. And this portion is going to be in our signal going into our 5-2. Okay, I'm going to tie in this guy right here into this part of the circuit. There we go. And the way that I'm going to describe this is that this is our restrictor, and this is our resistor, and this is our capacitor. So we're going to create something similar to an RC circuit, in that this resistor is going to limit the flow to our capacitor. Once the capacitor gets to a certain pressure, then the signal is going to travel through to the 5-2. Okay, this is a one-way flow control valve. We can change this to an off delay by flipping this component around. Remember, this is like a check valve with a flow restrictor component in it. Okay, so let's hit play and see what happens. Excellent. Okay, so we have the air coming up in the rest position. It's in the retracted position right here. And then hitting this push button will allow the air to come up. It will seat this ball. We'll have to go through this flow restrictor. That flow restrictor will determine how fast this charges up. And then remember, this is a closed circuit, so any pressure that's in this tank will also be in these lines. That pressure has to build up to a pressure that's greater than the spring. Once it's greater than the spring, the 5-2 will change state, and this will extend. So now we haven't changed the flow restrictor whatsoever. So it's wide open right now, and if we hit this push button, changes state. Okay, so it took 1 or 2 seconds there in order for it to change state. If we want it to be a little bit slower, then, and you can see that it looks like we have an on delay and an off delay on this guy. So that's the issue with this this simulator, is that we're trying to show an on delay timer, but by changing this value right here, sometimes the simulator isn't going to work exactly how like we'd have out in the field. So let's double check. This is open 100%. So let's bring this down to maybe 25%, and we'll see how that affects our circuit. So we're going to hit this push button, builds up pressure, then eventually when that pressure gets to a value that's greater than the spring, then it changes state right away. Excellent. Now when we let go of this push button in the lab, that double acting cylinder is going to come right back. Let it go here in the simulator, it takes a little bit of time. So there's no way around that in the simulator, not that I know of. If you do know of a way to do this, then put it in the comment section. But again, once we do this timer here, you can see that the air is going to travel from 1 to 2. It's going to come up. It's going to seat this ball. That air will have to go through the flow restrictor. That will slowly charge up our holding tank. Then when this guy gets to a pressure then greater than the spring, this will change state, and then it will extend. So we can provide that 5-second delay by changing how much that flow restrictor is cranked down. Once we let this push button go, then you can see that there's a clear path for that air to exhaust. So any air that was trapped inside the cylinder is going to be able to come down. Then it will go over here. We'll have full flow down here and exhaust out of 3. So in the simulator, it's working nicely for the extend. Nice delay here. Excellent. When we let this go in the lab, it'll come right back. In the simulator, it's taking a little bit of time for that to come back, but it will come back right away in the lab. All right, guys. So you can write this guy down for your on delay time. This component right here around, and you'll change it to an off delay. Let's take a look at this in the lab first, and then we'll switch it up in the next video.
Well, an external power.
Okay, so what we got here is a purely pneumatic counter. So it works purely off pneumatics, no electrics involved here. So that's what we just got wired up. We have 4 ports that we can work with. So P is just coming from our manifold. It's our primary. So that's our air supply going in. A is going to be our working port. So at the moment we have our count set to 19. So when 19, when it drops down to 0, counts down to 0, A is going to become active and allow air to flow through it. And then we have 2 of our pilot ports, Y and Z. If you want to see what they do now in a second. So our count set to 19. You can set it away. You do it by holding down this button here, and then you can set your counts, get your counts just whatever it needs to be. So we're just going to keep it at 19. Set that back to 0. Unfortunately, you got to go the whole way through it. We must keep that kind of override button in place. And then what happens here? If you hit C, it'll start giving a signal that will count down for you. Note, must get the air in a pulse. So it must be released before it's counted. So it'll go on and off. What Y does is it resets it first. It resets back to 19. Z counts it down. We can also manually reset it here. I'll bring it back down to 19. And you'll see when we can count, we get the 19 pulses. And all you need to do is you reset your air goes off, and we're back to 19. Then note when I count down from 19, come on, continue to count on down and just keep running it out.